Hey guys, welcome back to FEADITH Technologies. It's been a long time I didn't upload new videos. So if you're new to this channel, please don't forget to like, share, and subscribe. And in today's video, you know, these days I didn't upload any news videos because I'm very busy right at the moment. So I usually only upload the video because I have urgency to do that. For example, this Tuesday I'm gonna train several scientists. Yes, train several scientists from national lab in my country about modeling adhesive joint and composite. So now I'm preparing, I'm practicing training to present the material that I'm going to present to them. So I'm thinking, why not just recording this as usual, and I'm trying to upload this to YouTube. Maybe it will be helpful for other people's like you are watching right now. So, all right. So without further ado, let's continue the video. So I'm going to simulate T-joint. So this series is going to be two-part. In the first part, we're going to model T-joint. So there will be a composite beam with another composite beam. And then we are going to tie them. We're going to connect them with adhesive, especially in Abaqus. We are going to use a cohesive surface to surface behavior this time. So hopefully this will be helpful for you, especially for those of you who want to simulate adhesive debonding, right? Like for example, delamination in composite. And then the second video will be like a refinement of the first video, where we will just focus on how to make mass transition in Abaqus. So we're going to do several partition. So this is advanced level, I think, in the modeling of the pre-processing, because you're going to do a lot of partition just to create a mass transition. Normal people usually don't do this. Normal people don't do this, right? Because sometimes you're too lazy. We use automatic meshing. But in the second video, we're going to do make some mass transition. But let's do first, okay? Let's create the first part. So this is gonna be like two part, the upper part and the lower part. But we're going to just make one part, and then we'll make two instances later. So if you're new in Abaqus, don't watch this video first. You need to watch other video, basic Abaqus tutorial. Check my other videos, because in this video I will not explain every step very clearly. I will just go through it quickly, okay? Click continue. So I think the length will be, I'm not sure, it's 2 millimeter, I think. So it's 50 by 2. So it's a 2 millimeter thick and 50 millimeter long. And then I'm gonna make the another one. It's 30 by 2. Oh, sorry. It should be 2 by 30, right? Yeah, something like this. And I'm gonna make how you call it, a fillet. 5. First we need to trim this and this. And then we need to, okay, like that, okay. And then we need to go here between two curves. Click the first, put the fillet radius 5 millimeter. And then you go here, you go here. It's a sharing vertex node. So you need to remove that, because you have separate lines here. Remove, remove, remove. And then you go here to here. Okay, nice. Press escape. And then you go here, fillet, and then put 5. It's already 5. Click enter. And then first line, second line, like that. And then if you do fillet, you can do another fillet, for example, like this. This distance is not good, right? I don't know why. Yeah, so press Ctrl Z, we undo. So what I'm doing usually is to use this offset. Instead of doing fillet 2 times, I'm offsetting this guy. Click done, and offset distance is 2 millimeters, right? Because the thickness is 2 millimeters. Okay, not in this direction, but in other direction, and then you click OK. So now you can remove again using the trim. Where is the trim? Here. Auto trim. You trim here, trim here. It looks nice, right? And then you click X here, and then you click done. So usually, normally, the specimen of the T-joint specimen or DCB specimen is around 20 to 30 millimeters. But assuming this is like half model, so I'm going to put 10, okay? Okay, so this is the model that we have. So if you're reaching here, that's good enough for you. This is L shape, and then to make the T-joint, we will make another instance of it. So, and then we will orient it so it will have the shape of T, all right? But before that, we are going to provide a pre-crack with length 20 millimeters. So we need to make a cutting here, a partition. In order to do that, we want to make a datum plane. A datum plane is a plane that you need, additional plane that you need as a cutting plane, right? So you choose here, but you don't want to offset from principal plane. To make it easier, we want to offset from a plane that we choose, offset from plane. And then you click here, you enter value. If the direction is wrong, you need to flip. And then if it's okay, then click OK, and then put 20, right? So the distance between this face and this datum plane is 20, okay? And then we will make a partition using that datum plane. You are using partition cell and use datum plane, okay? You need to click and hold to get these options, okay? Sorry, you click here and then select a datum plane, okay? Because now we only have one cell, so Abaqus will not ask you which cell that you want to partition. But if you have several cells in your model, Abaqus will first ask you which cell that you want to partition, okay? So in this case, let's just directly choose the datum plane and create partition, okay? So this part will be pre-crack, okay? This part will be the one that adhesively bonded by glue that you want to glue, by glue that you have, right? For example, epoxy or whatever you have. Okay, in order to make a good mesh too, here we need to do a partition here just to make sure that we have a good mesh around the corner. So what you need to do is basically, you want to do partition using cutting plane, define cutting plane. Okay, and then as I said before, now we have two cells, because we'll ask you which cells that you want to partition. You need to select and then click done. And in this case, I'm using 3 points, right? Which point to define the cutting plane? This one, and this one. You need to select three points to define a plane, right? Create partition, and we need to do it again for this one. 3 point, this one, and this one. And now we have how many cells? 1, 2, 3, 4. This is the upper, the vertical one. This is the transition, the corner, and this is for the pre-crack, and this is for the adhesively bonded beam. I think so far it's good enough. We control S, we save it. Let's call it T-joint and enter to make sure that we save our model. And then the properties now here. In this case, I'm going to teach you important points too. We are going to model with composite materials. So you click here, create materials, mechanical, elasticity, elastic. This, we're going to simulate this using the 0 degree composite. So the 0 degree will follow this curvature like that. Okay, we're going to assign a material for property for that, and there's a trick to that. Okay, but first let's put engineering constants. So I will assume that this is glass fiber polypropylene, because in my PhD thesis I'm simulating that we work on the GFPP, so I remember my mind the material properties, the numbers, right? You can use any other material property, carbon fiber, whatever you want, but I don't have the number with me to use other composite. So the one that I remember is for glass fiber polypropylene with the volume fraction of 46%, and the number was 34600, 4300, 4300. So we are assuming transversely isotropic material properties. So new one, two will be 0.38. 0.38. We did the test on the Poisson ratio using DIC. Check my publication if you want. And the new to 3 is 0.4. And then for the shear modulus, this is the in-plane shear modulus. G12 will be 1700. 1700. And for the G23, it's 1450. Okay, this is the elastic properties. Okay, we will not simulating the damage in the ply at this moment, because that's not the point of this video. We're just going to model elastic composite material, elastic and orthotropic. And if you want, you can do it, but in Abaqus, this hashing damage for composite will only work for a continuum shell elements. So in this case, we are going to model it using solid. So this guy, hashing damage, will not work at the moment. Yeah, but I heard that Abaqus is, they have a new material model for a composite. That's LARC-05, LARC-05. I think it's developed by Pino, Professor Pino in the Imperial College. Yes, I applied to him once, but I think it didn't make through. It didn't go through. Anyway, okay. What's next? This one, create section. This is solid, right? So solid homogeneous. It's typical. This is a sign section. So this is the section that we want, and you click OK. So up to this moment, it's very normal. Now what you need to do to assign a material orientation. If you're using a composite, you can use this too, but in this case, I want to use this one. It's just several options that you might have. And back then, when there is no composite layout, we use this for for orthotropic material, or for any materials that requires material orientation. It's not only composite, right? So some metals, for example, they have an isotropic behavior. Oh, I talk too much, I think. Assign material orientations. Click. Done. So click orientation. So this is important. If you just do like this, what happens is that the X direction is the fiber direction. So for the vertical one, the fiber direction is to the number 1. Okay. This is not what you want, because what you want is basically the fiber direction follows the curvature of your samples, right? So it has to follow the curvature. So in that case, what we need to use is discrete, right? So it will follow the discrete shape of your model. Okay. So in that case, you need to define normal axis and a primary axis. So the normal axis is the normal axis, the out of plane direction of your composite materials. And the primary axis is the fiber direction, is your primary axis. So in this case, we need to define those two. Click define. First, we call the normal axis as the third axis. That's just by convention. Usually the primary axis is the first direction. So which one is the third direction? The normal axis is defined by the surface. So the normal axis, the other thing, is the surface. We need to choose this. Click done. Okay, so this is the normal axis. So I want to say something here because I tried it before. If, for example, you have a very sharp corner, sometimes it will be error. Okay, it will cause error because they will have difficulty to, how you call it, to define the normal axis right at the corner, at the, how you call it, right at the tip of the corner, right at the 90-degree tip, the point, because at that point the, how you call it, the normal axis is, infinite. It's not defined, right? So just to make sure you have continuous surface like this, okay? Just to make sure that, so you can make it work. Okay, and then we need to define the primary axis, the fiber direction axis. It will follow these edges. So we need to click here. You need to press Shift to choose multiple edges. All right, now that's great. And then click Done. And then click Continue. Yeah, and then that's it. Actually, what you need to do is that's it. But for example, imagine that you want to slant it fiber direction a little bit, like 30-degree. What you need to do is the axis. You need to choose the 3-axis. And for example, if you do, let me zoom it here so you can see. If you do 30, it will slant it a little bit. If you change 60, it will rotate, for example. Yeah, but in our case, it should be 0. Okay, so click OK and then click Done. So that's it. We fully define our model as a composite materials. We fully define the elastic orthotropic modulus, and we also assign the local material properties, local material direction, material direction, local material orientation. Yes, they're the same. Come on. And then create instance. In this case, we need to create 2 instances. So make sure you do auto offset like this, and then you click apply, and then you click apply for the second one, and then don't click OK. Don't click OK. If you click OK, it means you create the third one. Just click cancel. Okay, so what we need to do now is basically just translate this guy to here and then do some rotations. So what I need to do right now is to do rotation first. I want this guy to be rotated, and this guy will be the axis of my rotation. 90 or not enough, so I'm coming back. 180. Okay, and then you click down. Okay. And then what you need to do now is basically translate instance. So I want to point out this is the instance that I want to translate, and then I click down or I press the wheel, how you call it, the wheel, the scroll wheel in my mouse. I click, okay, so it automatically will click done, and then I will choose this, and I choose this, move it here, click done. Okay, so now they're gray. So what we need to do now is fixing this surface, and then pull the surface up. Okay, and then we'll assign this adhesive behavior here, and step, and then create step, and then you need to do static general. Yes. Okay, and click nonlinear geometry because it will deform like in very large. So because again, I think if you watch my video a lot, you will see this. When you're simulating damage, the classical, for example, Newton-Raphson will have difficulty in capturing the solutions because you will have like discontinuous solutions. So you need to have stabilizations, right? So just choose this. This is the default. It's enough, and add the maximum increment that is allowed, and then put this -10 just to make sure the Abaqus can do a very small time increment. So just put this one, and then okay, good. This is the time increment that you allow. This is the minimum increment size because you might need to have to use Abaqus might need to use a small time increment to simulate the damage. And also you need to set this solution control because you're going to simulate the damage. You go to manager, this one, continue, and then specify time increment, change to 20, change to 40, and then you go to IA20. So what the hell is that detail? So I will not explain to you detail. You can read the manuals, but the idea is that when Abacus try to solve your problem, they do it iteratively, they do it incrementally, right? So the one before 10,000, if you remember, it's how many increments that you allow at maximum. So because sometimes when the problem is difficult to solve, the abacus will start to solve incrementally small. Okay, so they might have to give, like for example, a certain note that you gave, the abacus might need to do it in so many increments, very small increments, right? So the IA, in the other hand, or the IR or I0 is basically how many iteration that you allow abacus. So I should not explain this here at this moment, but anyway, so the idea is that, for example, by default, the IA is 5. What that means? So abacus try to solve a time increment 1, and then they fail. What the abacus do next is cutting this 1 second to, for example, 0.2 second. They try to solve with smaller time increment, 0.2. That means they cut the time step one time, right? From 1 to 0.2. They try to solve with 0.2. If they fail to, they will cut again to 0. They divide it by 5. So every time they cut the time step, that's called one cutback, two cutback. And then if they fail again, they cut again, 3 cutbacks. So by default, Abacus will only allow 5 cutbacks. How do you know if there's a cutback? Usually there's, if you see in the monitor, you will see 1U, 2U, 3U. U mean unsuccessful. So every time you have unsuccessful attempt, you do 1 cutback. So at maximum, if you are unsuccessful to solve the time increment that you're having 5 times, you do 5 cutbacks. Abacus will show you, oh, too many attempt has been made. This is error. Okay, but in some simulation where you have damage, this cutback is so normal. Abacus need to simulate with very, very small time step. So you need a lot of cutbacks, all right? So in this case, I enforce Abacus to do at least 20 cutback before you give up. By default, it was 5, right? So now I'm choosing 20 because I know the problem that I'm going to simulate is difficult problem. So Abacus, work harder, okay? That's the meaning of this kind of number, okay? Just to enforce Abacus, to do more iteration, to do more cutbacks, just to get the solution that we want. Because we know the problem that we are solving, including damage. Damage means that you have this rapid changing in solution. So it's difficult to capture if you're using large time increment, okay? Okay, I talk too much. Sorry, guys. And here, there's another important thing, field open manager. This is edit. If you check my other videos, if you watched my videos before, I usually use evenly space-time interval because each frame output that I want should be spaced evenly, right? So I'm using 100 usually. But there's another way. For example, I will not explain why, but I want to use every n increments, right? So every 5 increments, I will try to put it. I will not explain here because this is going to be a very long video. I will try to explain this in another video. Okay, just too many things to say in this video. Okay, and then the energy, because we're using damage, not energy failure. We're going to simulate SDG for the damage. This is we're going to use quadratic quads. Okay, and I think that's it, right? Yeah, I think that's it. And then you click You click OK. I think, yeah, you click OK, that's it. Yeah. And for the energy, just in case you want to plot the energy, you already have the energy. Make sure you have the same increments 5, just to make sure you're sampling your data at the same point with your fill output, right? So it's always better to have the same setting for the history output and for the fill output. Interaction. Okay, this is where you define your adhesive bonding. You need to use this. You need to define your interaction properties. The contact. Continue. We are going to use. I forgot cohesive behavior. Okay, how is the behavior? So if I want you to try, I will not try in this video. If you use the default value, it will not success because sometimes the stiffness that Abaqus use is too big, so it will cause convergent difficulties. In my case, I'm going to specify the stiffness coefficient with the value of 100, 100, 100. So when you're modeling zero thickness cohesive behavior, your K theoretically should be infinite, all right? But there is no infinite in computation, right? You should have a number. So what you need to do is to put a value that is big enough, right? Sometimes people put like 10 to the power of 8, 10 to the power of 6, something big. But if you use the default value Abaqus use, you will fail. Yeah, sometimes it will not converge. So what you need to do is basically to use a low value like 1, try 10, try 100, check where's the maximum you can get, but at the same time maintaining your simulations can still converge, right? So here I tried, if I use 100 it will still work, 200 works, 300 works, 400 works, 500 it fails. So the maximum value I can use is around 400 to 500 maybe. Okay, so in this simulation I will use 100, but you can try, you can even try what I just said, try to use the default. Maybe you can do, I mean, it can converge, I don't know, but I tried before. And then if you want, this is like the behavior before any damage. So this is just elastic. So and then you want to put damage initiation. So for example, for epoxy, it will usually fail at 29 or 30. In shear, maybe 30. Usually it's harder in shear, but I don't know the number. This is for epoxy. So it's basically your GF50 is bonded with epoxy. And then the criterion, you can use the quadratic traction is one of the best criterion for initiation because you can account for, how you call it, for interaction between stress, multi-axial stresses. So there is interaction between sigma 11 and sigma 22. If you use maximum nominal stress, there is no interaction. What's the meaning of interaction, Dito? So I don't have it here. So imagine in one direction, my failure is 30. Maximum stress that I can attain is 30. In the second direction is 32. So imagine now I load it until 28 in the first direction, 28 in the second directions. If I use this guy, it will not fail because in both direction, it's still 28. The failure is 30. But it's strange. Like imagine you're pulling your materials in this direction, just like 85% of the maximum stress that it can attain. Of course, it will fail, right? Yeah, because there's interaction. There's interaction. So to account interaction between stresses in several directions, this is what you should to have. Okay, quadratic fraction. Okay, and then specify damage evolution. I don't know. I'm usually using energy. You can use linear. Okay, and then if you use a mixed mode 60, one of the most famous in BK model, Benzega K9, and specify the BK. It's ranging from 1 to 1.5, sometimes below 1. but the value that I'm using is usually 1.4, and then you specify your fracture energy for each directions. So in this case, I forgot what did I put. I think it's one. I'm not sure. One. Maybe. I'm not sure. And then specify the stabilization. It's a 0.01. Okay, it's you check my other video. I explained this. Basically, you need to stabilize. This is the viscosity. I will make special video about viscous regularizations, and for the moment, just believe me. Okay, click OK. And then we assign those properties, create interaction, surface to surface, click continue. Okay. Okay, you want to choose something, right? So we need to remove the cell. Remove cell, so you can choose this guy. Okay, you click done. And then select done. Select the surface. The surface is this guy, only this, because this is the pre-crack. They will not be connected, only this. And then you click done. Choose the sleeve type, the other type, click surface. You want to choose the other part, so you want to invert, okay? Now you go here, and then you choose this, and then you click done. And then I think this cohesive behavior only works in small sliding. I think you tried, okay? And only work with node to surface. And then the properties already chosen by default because you only have one properties. And that's it. I think it's okay. Now you can show it again, both of them. Yeah. Okay. So it was all right. I think, yeah. Okay. Okay, and then the load. The load is simple. You can click here, boundary conditions, displacement, continue. You choose here, you click done. 1, 2, 3, 4, 5, 6. Okay, basically pull, like in the machine. Okay, and then you pull. You choose here. Okay, click done. Pum 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 pum. But here in the Y direction, you want to pull something. I don't know how much I should pull. Not sure. I forgot the one that I put in the training module. But I think 50 is not 50. Yeah, just put 50 millimeters. Okay, and then we mesh. Okay, this is a mesh. So how you are going to mesh it? Just basically here. So this is what I told usually. So if you're modeling composite at the coupon level, usually the mesh that is suitable for the typical epoxy or typical composite should be around 1 millimeters. Okay, 1 millimeters. So yeah, this is good enough. If you want, you can use a lesser one, the smaller size, and then you click here, mesh part, and that's it. This is nice, right? If you want to, for example, you think that in this thickness direction you need to add more, you can add more by number. Maybe you want to specify the number directly. Okay, and then you click okay. Now you now have 6, right? Okay, and then if you go to assembly, it's already mesh because you when you create it in the, how you call it, in the assembly, click here, you where was it? I think you create mesh on part, right? There was an option mesh on instance or mesh on part. You click mesh on part. So when you do mesh, you cannot mesh in the assembly. You mesh on part. You need to go here first, and then you mesh it here. So once you mesh your part, it means that you mesh your whole instance. In this case, we have 2 instances, and both instances has been meshed like this. Okay, that's great. And then make sure you assign element type. you need to go to the part right again, because you mesh on part. So every setting of the mesh should be done in part. So it's 3D stress, reduce integration if you want to circuit order accuracy, enhance to for our gloss control, right? And then click OK, click done. You might think, Dito, we don't use element. No, we use cohesive interaction here. So there are two types of modeling approach that you can do when you want to model the adhesive bonding in Abaqus. Either you use cohesive surface to surface contact behavior, or you can directly draw an elements there and put cohesive elements. I did that tutorial about cohesive element before. You check in my other videos. But in this case, I'm using cohesive surface to surface. Okay. And then you go to job, you create job and say join C01, because we're going to have a second part. And then put 6 core, I think, because it's going to take us some time. So click submit. And hopefully we'll finish soon. Oh, at least it's running, it's no error. So it's a good sign. Warning is typical in Abaqus, okay? So typical. And as long as you don't have error, that's good. And because my computer is an old computer, it's gonna take some time. It's raining outside, guys. Okay, why it takes so long? Should I pause my video or no? Okay, I don't need to pause my video. I'm drinking, what is this? MACD? But don't drink, this is not healthy. You see, this is the time increment. They start at 0.01 and it takes several 7 iteration. They do it again 0.01. It turns out that they don't need to do many discontinuity iterations. It means that it's too easy for them. So they try to increase the time increment for the next time. And then they require 2 equilibrium iteration. Still too easy for them. So they increase again 0.02. Still too easy for them. And now they try 0.03. It start getting harder. 2 equilibrium equation, but with 2 discontinued iterations. This is how you read it. The total time now that is solved 0.09. We simulated 1. If you check the step, we set the time period 1. And now they try to increase to 0.05. It's getting harder with 3 equilibrium iteration and 10 several discontinued iterations. So it's getting harder in the discontinuity, in the contact region, in the tie region. So the total iteration 13, so it's getting difficult. They might, if they fail to convert, they might do cutback here, all right? That's what I say. If they cut the timestamp, that's 1 cutback maximum. They can cut 20, in this case, 20 cutback sequentially. The default value was 5. Oh, they are now increasing in 0.07. It's good. Total iteration 14. At one point, they need to cut back, I think, especially when the crack starts to propagate. All right. It's been a very long time I didn't upload a new video, recording new videos, so I'm too busy making things I should do. You see, they're now increasing 0.11. So it's getting more difficult. 23 iterations. At one point, they will fail. They need to cut the time step. See? It's still very easy for them. I don't know why. We almost finished like 67%. I didn't expect this, honestly. Yeah, 84% they finish. Maybe we make, because we use too small K 100. Oh, yeah, it's finished. Good. Completed successfully. You click dismiss. You check the results. Yeah, what happened? See, it's separated. Oh, 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 oh. Dum, dum. In the second frame, it's always finished. Oh, this is what I didn't like. We put by increment. Okay, this is my mistake. Yeah, but that's the result. So let me explain. Uh, we use every one frame. Uh, you export one frame every 5 increment, but we don't know how many seconds for that one increment. For example, if you choose this, check the first increment here, the 5th increment here, right? This is the first, and then the next one is the 10th. Already too large, right? Because your time increment is not evenly spaced, right? It depends on the convergence speed of your simulation. All right. In that case, I will try to limit my time step, maximum time step. I don't want my increment. At least give me, if the total period is 1 and I want at least 20 frame, so this is my maximum. Okay. Yeah, I think no. No, 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 no. If I want 20 frame, if I want 20 frame, no, I need to change. Let's check here. Let's check this guy. Oh yeah, well, no, 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 no. You might confuse what I'm thinking. So now we only use 12 increments, right? Why? Because we let Abaqus to flow as they want. They can jump like 0.17. Now we are limiting Abaqus to jump maximum 0.05. So at least they need to jump to do increment 20 increment at least. Was it 0.05? Where is it? Yeah, it should be. Let's make it like this. So at least they do 100. So they do at least 100. And for each 5 increment, they put 1. Okay. They put 1 output frame. And then let's make it harder. Let's make it the K. Where's the interaction? 100 is too low. Let's make it maybe 400. Oh no, let's make it 200. 200, 200. Okay. So the higher the number is better, because theoretically it should be infinite. Okay. Otherwise, you create spurious compliance problems. It's like you're connect. I don't know. Even if I explain like that, you might not understand. I will make a separate video, but the idea is that before you have damage, the the adhesive already having a stiffness of K. This is spurious stiffness, a stiffness that shouldn't be there. So that's why theoretically the stiffness should be infinite, but you cannot use infinite stiffness in your abacus, in your finite element solver. You need to put some number. So you need to put a large number as much as you can. But in this case, if you use a very small number, we create additional compliance to this bonding that shouldn't be there. Okay. Okay, this is what I said before. They start from 0, 1, they need 5, and then they start to increase, right? Because they think, oh, this is too low. They can jump 0.17, as we said before. So 0.01, the one that we put, is too easy for them. Okay, and then you see here, now 5, we have one output. Now for 10, we have 2. Now 15, we have 3 frame, right? And in that case, we can see how the crack propagate. And yeah, let's wait a little bit. So tired. Guys, don't forget to like, share, and subscribe this channel. It really motivates me. I try to, as much as possible, reply to the comment. Many people wants me to upload a video on several series like Abacus Python series. Please upload new videos. Yeah, I know, I know. I really want to upload new videos. Some people said, "Oh, please make a series about you, man." Yes, I really want. That's on the plan. But I'm very busy at the moment. Especially this is end of the year. Many people wants to do some kind of courses. Because they have this budget. This budget has to be spent by the end of the year. Otherwise, the government will not give them the same budget next year. So basically, they need to spend the money before the end of the year. That's why usually at the end of the year there are so many trainings requests coming to me. Yeah, that's why I upload this video, because I'm preparing this for the training. So I upload, for example, a video about I forgot, like impact and composite, because I have a student who works on that. So I want to teach him. So I make a video for that so he can watch it. I also make another video about many things, many things. That's because of someone needs that. My student, other people wants to pay me for training, right? So yeah, in some cases, if I have free time, I will try to upload a video that how you call it, that align with my idealisms, right? Yeah, I want to enlighten people, but in many cases I don't have time for that. That's why I upload videos based on the urgency of my needs, like this one. But I fully, hopefully, this also will be useful for you guys. It's gonna take a very long time. Sorry for my talk, guys. So, okay, I should have 4 frames, right? Because it's 20, 5 each frame. The beginning, 5, 10, 15. The fourth frame, yeah. There he goes, the fourth frame. Okay, let's me save. So let's should we? No, I should finish this video first. Or you want to be in the one video? Okay, let's do it one video. Let's do it one video while we are waiting for these simulations. Let's make the second model. We copy the model with model 2. So we finished the first model. They're running right now. Now what we are to do is that we are going to do some improvement in our first model. Basically, how to create a very fine model. Very, very fine model. So this is what I'm talking about. Let's go to mass assembly. Here, this is the crack tip. Imagine you want to measure something in the crack tip, like K1 or whatever you want to measure, or you want to measure the stress intensity, or you want to really, really, really simulate the crack propagation accurately. You want a very fine mesh. How you do it? You cannot use this seed part instance, right? Because it will make every mesh very small. So what you need to do is to make a transition mesh. So at this moment, I'm going to use this chance to teach my student. Actually, because I have a lot of students who use Abaqus and they don't know how to do mesh transition in Abaqus because it is not straightforward. If you use software like, you call it HyperMesh, yeah, I did HyperMesh. It's really easy to mesh. You can very easy, very easy. But Abaqus sucks for that part, so you need to do it manually. So let's check first. Let's check first. So imagine I want. Let's check the size. Where is it? Tools, query. It should be second part, but I will combine the video. Let's make a very long video, 2 hours. But you learn something. This to this. So the size of the elements is like, yeah, I don't know how you call it, 0.3 millimeters, 0.3 millimeters, and you want to make smaller elements there. All right, so 0.3, it's 1. Okay, so let's do it like this. Oh, let's do it like this. So what you need to do, you go here, and how many times? 4 times smaller, maybe, right? Maybe. So you want to make another datum plane 2 millimeters away from this guy. If this guy was 20, now let's offset 22. 21 and 22, I think. Yeah, let's make 21 and 22. Let's define this. Okay, you flip. Okay, 21. Okay, not 21, or maybe the second one. Enter. Click OK. 20.5. Let's make it like that. Okay. You might not understand what I intend to do, but just follow this. I think it's worth the wait. No, not this one. Using datum plane. Threshold and choose this one, and choose these cells to partition. Choose this guy, create, and choose cell, done, and create again, and choose this guy again, and create partition, and you get it like this, right? So what should I do? Okay, so now what we want to do is to sketch here, okay? And what we need to do is to do here. Partition face. Okay, and click here. 2 of them. Click done, and then this is in the right side. Okay, nice. So what I want to do is basically, I don't know this guy here, all right? And then I want to, this distance to this distance should be 0.25, right? Yeah. All right. And then let's make another one here to here. I press escape and then make sure it's uh 0.25 to enter. I don't know why they are like that. Why they are blue? I don't know. Select and okay, just click. There you are over constraining them, but it's okay. So the next thing I want to do is basically this is pop, pop, pop. Let's make in the middle. I think are they symmetric? Yeah, hopefully they are symmetric, right? Yeah, you need to do it. Let's make it professionally. Let's make this guy and this guy 0.25 to okay. So imagine no the anyway, let's make it like that. So let's make it like this, but make sure that this distance to this distance is now 0.125 in the middle. Okay, so then let's make this guy to this guy here. No. They're vertical, right? But make sure the size is good. Just follow me while we are waiting for the simulation. Okay, this is nice right now. So what you want to do is to take this. Okay, so what I want you to do is basically to copy all this guy. Is there any pattern here? Yeah. How to do it? Uh, let's remove this guy. I don't like this. Okay, and then let's trim everything. Everything. I don't need this actually. I forgot. Sorry guys. If you follow me, sorry. Sorry, but this is all I need. Okay, so what we need to do is basically choose this guy, choose this guy, choose this guy, and choose this guy. Okay, and then make a spacing of 5, 0.5, I think. 0.5. We want, do we need spacing? No, zero spacing. Uh, was it 0.5? I'm not sure. Number direction 1 is the right. We need to flip 0.25. Yeah, right, it was right. Yeah, and 0.25 in opposite direction. You go top, and then you click OK. Nice. So this is seems quite complicated, but actually it's not complicated. Once you know the pattern, what you need to do is doing like that. Okay, and then you go, you trim. Oh, we shouldn't. Okay, and then you go like that. Uh, why I get confused? No, yeah, I shouldn't get confused. Yeah. Now you know the pattern, I think, right? You go like that. and then 1, 2, you go like that, and then you go like that, and 1, 2, you go like that, and then you go like that, then you go like that. Okay, and then you can trim it. Auto trim. I don't need this one. 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 And tap tap. Oh, I made mistake. Tap tap. Yeah. What should I do? Oh, this one. Okay. And this one, right? And this one. Okay. Okay. If you do it like that, you make one transition. Oh, and I don't like this guy. Sorry, guys. This you guys can remove it. Let's remove this guy. Okay. So now one element becomes, no, this is wrong. This is wrong. Yeah, one element. Oh fuck. Am I doing mistake here? Yeah, this is one element. And it becomes two elements, right? Okay. Right. And this is two. Why I get confused? Let me think. Maybe like this. No. I'm so stupid. Oh, I'm old now. Can't even think about it. Okay, why? This one element, it goes to doom, and it should be doom. All right? No, it should be all right. Oh, it should be like this, maybe, right? Oh yeah, I shouldn't have this one. Sorry, guys. Where was it? Here. Ah, yeah. Ah, yeah. Ah, yeah. Nice. I don't have this one. I don't like this one. Don't like this one, right? This is the pattern that you're looking for. So go one goes two, one goes two, one goes two. All right, do you agree? Now you want to do it again for each one here. You goes to four, you goes to two. Okay. Okay. So now I'm sorry if the video is long, but it's worth the wait. Abaqus should have automatic way in doing this because this is nice. This is something that we need to do in our research, mass refinement. But Abaqus make it difficult because we need to do it manually. Or you can add scats, you can save it and you can add scats if you want. If you want to reuse it later. First, now let's remove one line here. Oh no! Oh no! Let's. Let's make it like this. Okay, it should be going here, and it should be in the middle. Okay, so this should be 0.0125 divided by 2, right? Oh no, how much should be the length? I'm not sure how much the length would be, but imagine, I don't know how long is this guy. How long is this and this? Yeah, 0.12. Okay, so this should be divided by 2, right? This and this should be 0.125 divided by 2. Yeah, but they're not connected. Oh shit. Okay, anyway, suppose that this is same size. This is what you need to do. Again, this, and this. Okay, so why I confused? Oh, yeah, you, this is 1, 2. This is 2. There should be 2 or no? There should be another one here. Sorry, guys. There should be another one here in the middle. Fully. Let's check the size. 0.125 divided by 2. Then you enter. And then why he moves? I didn't like. Imagine this is right, but it will not be right. I don't like this. It has to be systematic. Oh shit. Okay, to make sure this guy didn't move while let's make constraint. We fix this guy. I hate to do this actually. Too many things to do. 1, 2, 3. Click done. This is I don't know. This is the weakness of Abaqus. Just to do a simple like this, we never know which one is moving, right? 125 divided by 2. You see, it moves everything. Why the? Control Z. That's from here to here. 0.125 divided by 2. Okay. Nice. And then let's make this to this. Same thing, 0.125 divided by 2. Or over constraint, so you don't need. Okay, so now they're good. Let's delete unnecessary things. This is unnecessary, right? Oh no. Let's make a trim first. Down, 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 down. And then we can choose this. Select this. Alright. We select this again. And down. Okay. And then let's make it better. You go here, you go here, you go here, nice. And then you trim this guy first. And then you trim this guy, right? And then you can actually draw it like this if you want. Draw, draw, and you trim it, the excess, and Trim it like this. All right. Trim it like this. All right. And then I'm too lazy to make the. Okay, I can trim this guy because I don't need. That's why I have that here. Okay, and then I can do it like this. Okay, and then I can trim this way and I can trim this way. So now I have one pattern, and then I can copy the pattern. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Done. And the spacing would be 0.125. I don't need many, right? I don't even need, but I need spacing downward. I think it's okay, 8. So now you go from this big to and this 4, right? So this is what we call transition, guys. And then you click done, click done. And then you want to do partition, you sketch. Okay. Make sure you go to this, then you go here, turn off perspective first so you can choose easily, and then you select cells to partition these cells and select edges in the same part. Okay, click done. Must lie in the same plane. Uncheck this guy. Oh, you cannot do it like that. You need to choose from the top, I think. So you need only to choose from here to here. Click done. You extrude along edges because you want to sweep this path. Create. Why? Oh my god, it's it's so tired. It's so tiring. I'm too lazy to choose this guy. Okay, let's do it. Select cells to partition. Okay, and by edge angle. Edge angle. There's no edge angle here. You're not having the same edge. Uh, pa 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 pa. Pa, pa, pa. Yeah, this is the correct tools. We need to be able to select them. I don't know why we cannot. I used to be able to do that. Let's choose again cells to partition. You press shift. My mistake is because I choose select cell to partition, click done, and one or more edges individually. I go here. Edge angle. Okay. Let's do it one by one. So tiring, but what can I do? Fuck, I will not do this. But I will do this. Too much. Give me a smarter way to do it, please. Okay, I can get it. Thank you. Hopefully will not choose anything behind. Okay, I think that's it, right? Oh, this one too. I think the interior part already. Click done. It lies on the same plane. Come on. Oh, I misclicked this guy. Okay, click done. Sweep along edges, and hopefully this will work. Create partition. Shit. Why? Why he didn't want to partition? Okay, anyway. Hopefully this will work. Let's go to the mesh. Let's go to the mesh. Okay, let's mesh it right now. They already have it 0.5. It should work, I think. No? What the hell is going on? Uh, it's in reverse, right? Okay, don't worry. We will make this one easier. We will enforce them to have, I don't know, by size maybe. This size is, I don't know, 0.125 divided by 2, if I'm not sure, if I'm not wrong. Right? Yeah. And we make them do not allow to change. So they should follow this. So this guy will match. Okay. Okay. You see, now we have a transition. Really, really nice transition. And detail, but the elements, it's not good here. So you can put, because we know that if you go to assembly, we know that the crack tip is only here, I think, uh, in the first datum plane, right? Yeah, this is the first datum plane. So what you want to have is that after the pre-crack, you want to have a nice crack tip here. You go to number of, I don't know, maybe eight, no, 4, at least 4. Yep. Or if you want more, you can use more. You can use 8 maybe to make more accurate result, especially if you want to capture the stress concentration. All right, Dito, but you might say, Dito, but I don't want very small, how you call it? Small mesh here because it's already behind the crack tip, Dito. So I want to return to this guy again. So what should you do? You just need to, how you call it? To mirror this thing. All right, you need to mirror this pattern. So let's do I will not ask you to do mirroring. No, I will not ask you to partition cell, partition face. Where's this face partition? I forgot. Set that on plane first, 1, 3. Where is the, this is the first model, second model. We're working on the second model right now. It's a part 1, features. There is partition face. You sketch, right? Edit, magic. This is the face that we want. Now we want to revert it back, right? So what I can do, I can do mirroring. Should be easy, right? To do mirror. Where's the mirror? Here. No. This one here. No. Translate. Here, mirror. Okay. So what I can do right now, basically, I want to copy, pick a mirror line. This is mirror line. Select entities to mirror. I want to mirror this guy. Only this guy and the internal part. And then click done. All right. So I'm done. Done. Okay. So let's regenerate, I think, the features. Why? Was it fail? The mirroring fail? No, right? Didn't fail. It mirrors. Yeah. Click done. Okay. Features regenerate. So why? Features part. Let's go to the part. Part features regenerate. Why it didn't want to regenerate? Let's remove the mesh. Maybe because of the mesh, but shouldn't be. It should be automatically regenerate. Or I don't know why. You understand, guys? Why? Let's see. Okay. Maybe let's make another line here. Let's delete this guy. What's this? Okay. Click done. Click done. Regenerate, please. Why? There's no regenerate here. This is really strange. Regenerates. I don't know why it doesn't want to regenerate. But that okay. I get it. Because when we want to partition face, section partition face, we only choose these cells that you want to partition. Okay. So even if you have this sketch here, they will not regenerate. Yeah. Then in that case, let's remove this guy. Why? Let's save them. Save sketches. Sketch transition. So did I save it? Sketch transition. Okay. Now let's try to sketch here. Click here. Vertical on the right. Okay, now let's do it again here. Instead of taking this guy, we are going to add sketch transition. Okay. And how you call it? You click done first, but this is not. This should not supposed to be here, right? Let's delete this. I hope I can delete only part of it. I can delete it. Okay. Let's delete this guy. 1, 2. Oh, I want to delete these 2 only, not you guys. Okay. And now what we need to do is moving it here. Okay. Let's translate it. How to translate, guys? Here? No. Where's the translation? Auto, no, not auto trim. It's here. Okay. So you want to move. Not this one. Not this one. Okay. Click done. So I want to move these guys. Endpoint to here. Okay. Nice. And you click done. Click done. Okay. It's really nice, guys. So now go to the mesh. I think it works great right now. Okay, no. Now let's mesh it. Let's see if it works. Yeah. Now it works. But the video is really long video. Shit as shit. Sorry. Okay. But at least it's good right now, okay? You can, but the shape is not good, Dito. Yeah, you can do like this. Select cells to partition, right? Okay. And then you can try to just select this face, 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 face. Click done. And then you can along edges, this one. Create partition, should be easy. Right? And then you can try to do it again. Now it looks great as it intended, right? So that's it. You can do simulation again. Oh, you really need to save the sketch, right? I don't know where Abaqus saved my sketch, but I will not do it again in the future. Is there any way to save sketch, like saving the sketch file? It's really terrible job to do. Okay, and then let's run it again. What the hell? It didn't create instance? Oh shit. No, it should be. Because I mesh on part. Oh yeah. Mesh. Yeah, it's good. So we go to job. Now let's run the second simulation. Join fee02. It's a very long video, sorry guys. I didn't expect it will be that difficult to make a nice one. Let's make a core. Here's the first one. Let's submit at least one part of the region. Okay. Need to reselect this interaction. So let's remove the upper part first, like we did before. Remove, remove, remove. Okay, done. So tools, set manager. Oh no, not this one. It's supposed to be a surface. master surface. Need to choose individually. This is the master. And then the slave surface, you need to invert. All right. Okay. It's good. Right, mesh, job, and submit. Should be okay right now. While we're waiting for the second simulation to finish, let's check this result. Yeah, you can see right now. Yeah, yeah, you can see now that they are adhesively bonded, and then they start to delaminate. But you know, each frame they have different time frame, so you can set loop based animation time history, not frame based but time based. Time increment maybe 0. I don't know, 0.1. Yeah. So, yeah. So this is nice, right? Very, very nice. Because this one is actually too easy to converge. You can tell, right? 100 increment. So in that case, you can actually increase the K, right? Because it's still very easy to converge. You can increase the stiffness to get the theoretical stiffness. That is quite goes to infinite, almost infinite. Let's check first. Yeah, this one should be easy, I think. Okay, guys. Should we wait? I don't think should we wait, but you can already tell right now, or maybe you can already see the results. Or let's wait until 10, so at least we can see some crack propagation. Let's check this one, because if you see the first one, let's wait until frame 5. We already delaminated that far. Frame 5. Okay, and then we stop. I think you can already tell the difference. If we reach frame 5, now it's frame 2. So we learned a lot today, guys. First, we learned how to create discrete material orientation, the T-joint, right, adhesive joint, and how to plan for the pre-crack. We create datum plane, and then we learn also how to set the Abaqus solver to work harder, especially for the case where we have difficult convergence. And we also I teach you in a stupid way, but that's the way to do it, to make a phase partition, yeah, to phase partition in Abaqus and make this mesh transition pattern, right? Yeah, so basically the shape is like this. You go from one element here, you end up with 2, and then you go with one element here, you end up with 2. If you want to make the third, you can also do that. You go from 1 here, end up with 2. Yeah. So it's exponential, it's power 2, right? And it's really nice if you have a mess like that, especially if you want, for example, you have a contract problem. If you have a contact problem and you want to make sure that you have this nice transition, it can be easily done in a software like HyperMesh because it's especially a special purpose meshing software. But in Abaqus, the CAE is not really robust in doing that kind of stuff, right? So in the future, I'm planning, because I'm using HyperMesh too for several projects that we have. We have also the license for that. So I'm going to try to explore about that, to explain about that, how to use hypermesh to make a good mesh, especially if you have like CAD software, you want to do mist surfacing. That's very nice to do in hypermesh, but not in Abaqus CAE. So let's check again. Last one, still frame 2. It will make the third frame in 15. Let's go. Come on, come on, come on, come on. I think it's already, I don't know, 1 hour, 2 hours. I don't care. I don't care. As long as you watch it, I like it. Please like the videos. And yeah, I mean, it's good. I'm going to give a training Tuesday. Imagine if I don't practice this and I ask them to do it, and then they said, "Oh, we cannot do it. Please, can you do it?" And then I stuck too in front of them. It will be so miserable, right? So it's good that I practice here. Uh, I did this a lot before, but I'm quite old right now. Forget a lot. Okay, let's wait for the third frame. Once we have a third frame, I will end this video. Let's check. Okay, nice. Third frame already written. Then we go. Okay, you see here. Oh, it's too fast. I really like this evenly spaced time interval. Oh, no, I'm not time based, just make frame based. If you want to see frame by frame. Yeah. It's too fast, huh? Even for the first frame, it's already propagated here. You need to make it longer. This, put it here maybe. Okay, because this is too fast. Now it's not even in the crack tip anymore. But you can see the effect of this mesh refinement. Why? Because you see, there is a strange stress distribution because we have smaller element here. There's the maximum shouldn't be here, right? Not sure. I'm not sure this is due to the, I don't know. Yeah. See, it should be going down, but this guy still captured the maximum. Yeah, guys. If we want to compare, we can compare, but I forgot how to do it. Tile pivot vertically. I'm pretty sure we can open two ODB at the same time. Yeah, I'm sure we can do it. Let's try. Because I need to try for the training too. So imagine that you are in a training right now. Viewport 1. Viewport. Create another viewport. No. Where is it? This should be T-zone P1. Oh, no. Let's tile them. And then let's how? They're linked right now. Unlink them. And then let's put them like that. Eesh. It's not really easy to control this Abaqus CAE. You guys from Abaqus, you need to work on with this, okay? You need to work on this. Thumb, and you go here again, thumb. Why can I maximize this? Okay. Wait, I need to link you guys. Let's go to initial. Let's go to initial. Let's go link both of you. Okay. You see. 1, 2, 3. Why? Why I cannot like the same skill? It was strange. Yeah. I'm not sure which frame is this. It's increment 15. It's the same increment. Now link them. Let's link them. Go back to the maximum is 39. This one is 31. You see, this is the effect of mesh refinement. It's 29, 27. This is 28. This is 30. This is not finished yet. You see, so mesh refinement is really important. That's the point, especially if you wanna. I mean, if you're doing for publications, you don't want to make a conclusion based on the model that has not a proper mass. Especially when you have a crack, you need, at least in the crack tip, you need to make a fine mass. Okay, so guys, thank you for today. I think it's quite good practice for me before I go train scientists. Because I'm not training students, I'm training scientists who get their master degree already. So yeah, thank you very much. Don't forget to like, share, and subscribe this channel. I'm trying to upload regularly if possible, if I have time. Otherwise, in case of I have urgency to do something with Abaqus, I will try to make the video at the same time and upload it on the internet because maybe many people will learn from it. So without further ado, bye.